Hi everybody. Today my discussion topics is beam element stiffness matrix. On a beam, if we apply loads, then beam suffers displacement and rotations. These fundamental characteristics governs the behavior of elastic structure. That's why we need relationship between applied loads and the displacement, and it can be expressed as, we can see it here, force vector, displacement vector, and the stiffness matrix. So let's see. F means it is the element and force vector, and K, it is the element stiffness matrix, and delta, it is the element displacement vector. So we understand now these three terms. So let's move ahead to understand more details of it. Here I am considering an element with only 1 degree of freedom, and the matrix and vectors can be written, say, as this one. Also it can be rewritten as this: K equal to F by delta, or F over delta. And this equation would lead us to a definition of stiffness. Here I have written the force necessary to maintain a unit displacement. Equation tells us very clearly how unit displacement will come. I mean, as it is in the down, I mean denominator, so surely per unit displacement, this force. Now for this column, say I want axial stiffness of this column. So if I want axial stiffness of this column, we can derive it from the standard relationship. As we know this relationship, elastic modulus equal to stress by strain, and expanding at an end we can write force equal to EA over L multiplied by delta. Here all the this column's dimensions is given L, and here also we can see it here, this delta. If we press force here and here, it will be compressed, and cross-sectional area A. Now this equation, F equal to EA over L multiplied by delta, how we will understand if we apply unit displacement. Say unit displacement, when we put delta equal to 1, our equation appears as this: if we look at this definition, surely we know this is nothing but the stiffness. And this is the force also. Force necessary to maintain a unit displacement. Already I assumed unit displacement. This force is necessary. How much it is? EA over L. So surely this is stiffness. Very simple. Now let's move to understand how to handle the 2 degrees of freedom, because this is 1 degrees of freedom. We are considering here a beam element of length L, Young's modulus E, and cross-sectional area is A. And this beam, it is subjected to axial forces F1 and F2 at this end, I mean node A, and at this end it is node B. Now if we assume that the node A, it is displaced at a distance delta 1 in the direction of the longitudinal axis. Longitudinal axis, it means it is in the direction of X. And similarly, node B, it is displaced at a distance of delta 2. Now, if we want to get force displacement relationships, how to get that? This is the thing. How it will be? This force equal to AE over L, and this will be change in lengths. But make sure delta 1 must be greater than delta 2. We have to assume this. Then only we can write like this. So we got the relationship, force and displacement relationship. Now, say with more expansions, we can write it, say F1 equal to like this, and it is, I am assuming it is equation number 1. So we got F1. So how to get force F2? This is very simple. Say assuming equilibrium in the X direction. If we assume that equilibrium in X direction, so the relation between force F1 and F2 must be like this. So once we get this, we can find F2 only replacing F1 at this equation. So it takes this form. Expanding, we are writing as this. So we got 2 equations. Now, if we go for using these 2 equations to merge it in the matrix form. So let's see how it looks. In matrix form, it gives us this. Here, this is force vector, displacement vector. This is the stiffness matrix. 2 by 2. 2 degrees of freedom means our stiffness matrix will be 2 by 2. Already we understood this is the stiffness, 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 and it is all a element of stiffness matrix. So there are 4 elements in this matrix. Now we can write in short as this. if we consider this 2 by 2 matrix as this K, and this is delta, this is force, so force vector, stiffness matrix, and the displacement vector, and we can call this element stiffness matrix. So we are now clear with 2 degrees of freedom. Now let's move to handle 4 degrees of freedom. Our discussion already so far has been restricted to structure comprising member capable of resisting axial load only. But in this case of rigid jointed plane frame structure, the loading generally consists of axial, shear, and bending forces, and the effect of which must be determined by axial, shear, and bending effects on this element. And once we assume that, we can derive the stiffness matrix for this beam. So in this figure, we can see a beam, it is uniform beam of flexural rigidity EI, and length is L. And the x-axis, here I forgot to write x, but this is x-axis. It is taken parallel to the axis of the member, and a positive y-axis is taken perpendicular to the x-axis, and a positive sense of rotation is determined using standard right-hand rule. Also, we can see that node numbers are assigned to the end of these members. It's very clear. Here, beam nodes are designated. This is a very important point. Beam nodes are designated as the locations where forces are applied and where displacement are measured. Very important point to understand. These beam nodes are designated as the location where forces are applied and where displacement are measured. So from that point of view, we can see here this beam is subjected to nodal forces F1 and F2. Very clear. And nodal moment M1 and M2. And it is in XY plane. Basically, the force applied at the nodes, very important point, basically the force applied at the node, it consists of, this is the real scenario, consists of transverse shears and bending moments. And due to that, the beam suffers nodal displacement. That's why I put here nu1 and nu2 as the displacement. And also it suffers rotation theta 1 and theta 2. One important point is I did not include any axial forces on this beam. So we can say that axial forces are assumed to be equal to 0. Now, here what you can see, the nodal, the forces induced in the elements by nodal structures and which maintains its displaced form. It is displaced. It maintains its displaced form. Also, we can write element end forces F1, M1, F2, M2. Now, this element end forces can be related to element and displacement. Let's see in the next slides. So this element and forces, as I said, can be related to element and displacement. So what we can do, if we look at this, so element and forces, as I said, can be related to element and displacement. Force displacement, we can create a relations. In expanded form, for these four forces, F1, F2, M1, M2, as I said, 4 degrees of freedom. So our this matrix K, it will be here 4 by 4. Already we learned before, for 2 degrees of freedom, we got stiffness matrix 2 by 2. So 4 degrees of freedom, it will be 4 by 4. So as per this, our matrix will be like this, according to this equation. Now, here we can see this all the forces, we can say it is a force vector. F1, M1, F2, M2. Force vector. This is displacement vector. And these two are related by stiffness matrix. And it is 4 by 4 stiffness matrix. Now, our target will be to create this. To generate this, what will be the value for all this stiffness coefficient. Because the column of stiffness coefficient, it is the set of forces and moments corresponding to the set of displacement and rotations. And through analysis, we have to get these 16 terms. So let's see how to get that. Very important points. As I said, the relation between joint forces and joint displacement are developed by how? Relation between joint forces and joint displacement are developed by, because our target is to get the stiffness matrix elements. So the relation between joint forces and joint displacement are developed by assigning the arbitrary value to a single component, because we had 4 components. 4 components we had. And when we will consider a single displacement component, in that situation requires all other displacement component to remain or to consider equal to 0. As an illustration, say this one. In this figure, here node 1 and node 2. So here node 1, we have taken arbitrary value new 1. It is equal to 1. Say here new 1 I have taken equal to 1. All other, already I said, all other will be equal to 0 out of 4. And this is the deformed beam. Here node 2 it is fixed. Now if node 1 of the member as it is displaced by new 1 relative to node 2, so that the chord of the member it rotates anticlockwise. Now the moment can be related to the displacement new 1. This is a very important point. Moment can be related to displacement new 1. How? We will get this moment m1 this 6 ei over L square by multiplied by new 1. We'll get this moment. Actually, in my previous video, I explained how we get this value. But here I am showing directly the value of moment and force. This one we got m1. So here it is a fixed end. So there is a moment here m2 and force also is here f2. I did not write here, but you have to think of fixed end means here there is a moment and there is a force also, and that is m2 f2. So what will be the m2? M2 will be this. So once we get these two, surely we can find F1 and F2. How to get F1? F1 will be adding these two moment divided by L. If you add these two moment, then divide the result by L, you will get this. Same way we will get F2, only difference is here there will be negative. So we got the 4. This is actually, these 4 elements constitute the first column of matrix K. Say this is the matrix we are intending to get. So our first column is this one, K11, K21, K31, K41. So these are the, this is K11, K21, K31, K41. So these, it is, we can say these 4 elements, it constitute the first column of this 4 by 4 matrix. Now let's move. Now we took new 1 equal to 1. Now next we have to assume this theta 1 equal to 1. Here also at node 1, what we have done, arbitrary value, here we have consider this theta 1, it is equal to 1. We have to assume, before we assume this new 1 equal to 1, now we are assuming theta 1 equal to 1, but other 3 will be 0. Now this is the deformed shape, deformed beam. Here same way node 2 is fixed. Here actually I showed moment and force, so it's very clear. Now if node 1 of the member is displaced, it is rotated. If node 1 of the member is rotated by say theta 1 equal to 1 relative to node 2, so that the chord of the member rotates anticlockwise. So the moment, of course, it is related to this theta 1, and we get moment as this 4ei over L multiplied by theta 1. And once we get 4ei over L multiplied by theta 1, so surely our far end moment will be 2ei over L. Once we get this 2, it means we can find now other 2. How to get that? Now these 2 will be added, and another important points, the applied moment M1 and M2 are in equilibrium. These very important points. Whenever we go for finding the F1 and F2, we have to consider that the applied moment M1 and M2 are in equilibrium with the reaction force F1 and F2. Then only we can make these relations. So F1 will be very easy, this plus this plus this divided by L, this plus this divided by L. We will get F1. Again this plus this divided by L, we will get F2, but there will be negative sign. And these 4 elements constitute the second column of matrix K. How it is? Second column, it means K12, K22, K32, K42. This, K12, K22, K32 and K42. So we got the second column. Now let's move for finding the third column. Here we are at now node number 2. Before we were at node 1, now we are at node 2. And arbitrary value, this new 2 equal to 1. We have to consider this now. New 2 equal to 1. All other 3 will be 0. New 2 equal to 1. And this is deformed beam. Here node 1 is fixed. Now if node 2 of the member, it is displaced by new 2 equal to 1 relative to node 1, so that the chord of the member rotates anticlockwise, and the moment can be related to displacement nu 2, same as before. And we get M1 equal to minus 6ei over L square multiplied by nu 2, and m2 will appear minus 6ei L square nu 2. So the applied moment m1, m2 are in equilibrium with the reaction forces F1 and F2. Only then we can write F1 equal to this plus this divided by L. I mean this plus this, how much comes? Then we have to divide it by L, then we get this 12ei over L cube. Same way F2, we have to find this adding these two divided by L. So these are the values we got. Here we have to put minus, this is plus. So we got it. Now this is the third column of the matrix. What is our third column? Third column is this: K13, K23, K33, K43. I mean this one. K13, K23, K33, K43. Now we have remaining fourth column. Let's move to see how to get that. Here also we are at node 2 of the beam, and here our arbitrary value theta 2 will be 0. I mean theta 2 will be 1. Sorry, theta 2 will be 1, all other will be 0, because this is our last one for getting the fourth column of stiffness matrix. So theta 2 equal to 1, and it is deformed shape of the beam. Here node 1 is fixed. If node 2 of the member is rotated by theta 2 equal to 1 relative to node 1, so that the chord of the member rotates anti-clockwise, then the moment can be related to this theta 2, related to theta 2, and m1 in that case it will be 2 ei over L theta 2, and m2 will be 4 ei over L theta 2, because this is far end. Far end always it will be half of this. If it is 4 ei, it will be 2 ei. So once we get this, as we know, the moment and applied moment, here we have m1 and m2, and already I said in all three cases that these two moments are in equilibrium with reaction forces F1 and F2. So surely in that situation we can write F1 equal to this moment m1, this moment m2, adding these two, then result will be divided by L. Then we get this. Similar fashion we can find F2 equal to this. So one will be plus, another will be minus. So this is the fourth column of stiffness matrix. This one, K14, K24, K34, K44, 14, 24, 34, 44, fourth column. So we got all these elements. Now let's see how we can arrange this. Now all these terms, what we got, like totally we got 16 terms. Now these 16 terms we can write it as an equation. How to? Look, F1 equal to, we can write this equation. M1 also, we can write these equations. Then F2, then M2. As I said, totally is 16 terms. 16 terms we can write like these equations. Because first column, second column, third column, and fourth column. Now, let's see how to write it in matrix form. That's the points. We got this. This is actually force vector. So we can write it, it is force vector. Then we got this, this is the stiffness matrix. And this is the displacement vector. So our intentions here, force vector, stiffness matrix, displacement vector, which this one, stiffness matrix, which has 16 terms. So we got the stiffness matrix 4 by 4. I think we are done up to this.